Hi, I'm Ian.
And I'm Avi. And this is Lab 3 Gaussian Beam Imaging. The goal of this lab is to achieve a beam spot at least 10 times smaller than we observed last week. The equation shown describes the beam radius at the back focal point of a lens. You can see the radius is inversely proportional to the beam waist before the lens. So, to decrease the spot size, we could increase the beam waist. One way to increase the beam waist is to use a Keplerian telescope as a beam expander. The ratio of the focal lengths in the telescope give us the magnification of the beam. We chose a 16.5mm focal length microscope objective with an NA of 0.25 to be our first lens, meaning the second lens must have at least a 165mm focal length to achieve 10x beam expansion. To make sure we hit at least 10x, we decided to use a 300mm focal length lens as our second lens, giving us a magnification of 18.2. In addition to achieving a smaller spot, we also wanted to limit the spatial noise the laser may have picked up from optical defects and particles in the air. To do this, we can place a pinhole at the intermediate image plane in the beam expander. Because a lens does a Fourier transform, any high-frequency noise present before the lens will be pushed out to the edge of the beam where we can filter it. We want to choose a pinhole diameter that cuts out the noise, but also preserves the optical power of the beam. From the error function describing the radial power of the beam, we determined that a pinhole diameter 3 times the beam radius will preserve about 99% of the power. We inputted our parameters into the center equation and found our optimal pinhole diameter to be 21.8 microns. However, we did not have a custom pinhole maker with us, so we had to choose between the 4 pinhole sizes available to us. We quickly ruled out the 10 and 50 micron pinholes, as a too small pinhole would be difficult to align, limit power, and create intense diffraction. However, a too large pinhole would not filter out the higher order fringes. This left us to decide between the 20 and 25 micron pinholes. A slightly larger pinhole would be easier to align, so the 25 micron pinhole was just right. Enough theory, time to build our assembly.
First, we aligned two lenses with focal lengths of 300 and 200 millimeters to our optical rail. Then we placed the objective lens mount on the optical rail and aligned the objective pupil with the height of the beam. Once we observed the beam propagating through the objective lens and centered on the boresight iris, we placed the 25 micron pinhole in the mount to act as a spatial filter. The lateral position of the pinhole had to be adjusted in order to see the beam centered on the boresight iris once again. Fringes can be observed once the pinhole is laterally aligned with the beam. In aligning the spatial filter, we ran into an issue where the beam could not be seen going through the pinhole with high intensity and minimal scattering. We realized that we initially had the pinhole face the wrong direction, which was causing unnecessary stray light in our system. We want the spatial filter to be coincident with the intermediate image plane of the Keplerian beam expander. To do this, we adjusted the axial position of the objective lens until we observed the fringes are extinguished. At this point, the objective lens and spatial filter are assembled, and their position will be fixed for the rest of the assembly process. We gathered relative power readings before and after the objective pinhole assembly. We concluded that around 93% of our optical power made it through the spatial filter. The loss is most likely due to the outer edges of the beam being clipped by the spatial filter and Fresnel reflections from the surface of the objective lens. The 300mm lens must now be placed in the system after the spatial filter to once again collimate the now diverging beam. We roughly estimated the location of the lens to be around 300mm away from the spatial filter, then adjusted the axial position of the lens until the output beam size remained constant on a moving observation screen. The collimation of the beam can be checked using a shear plate interferometer. If we place the interferometer on the optical rail and input a diverging beam, the fringes will have a positive slope intersecting the collimation line, as shown on the left. A converging beam will show negative slope fringes, as shown on the right. The goal is to perfectly collimate our beam, which can be achieved by getting fringes parallel to the collimation line, as shown in the middle. As you can see, our collimation using the visual test was fairly close, but ultimately our beam was converging. With some small adjustments, we can ensure the output beam is collimated as indicated by the parallel fringes. We tested collimation with a 1-inch and a 2-inch shear plate. We found that the 2-inch shear plate was much more sensitive than the 1-inch version and contributed to a better collimation quality of our beam. Now we can add our previously aligned 200mm lens to focus down the expanded beam. With a moving observation screen, we can observe the beam converging to a spot, then diverging again. We use the knife edge scanning method from Lab 2 to profile the beam at 2 locations, one scanned before the beam waist and one after. This will allow us to calculate the size of the spot created by the beam expander assembly.
In addition to creating a smaller beam spot, we also cleaned up the beam. Here's the before, and here's the after. Here are results from the 2 knife edge positions. Our 2 measurements were 4 centimeters apart. We wanted to take measurements close to the beam waist so that the photodiode could capture the full beam before it diverged too much. We can approximate the beam radius at the back focal point of the lens as the beam waist because the lens was focusing down collimated light. To find the new beam waist, we can use this equation and solve for the Rayleigh range. Then we can solve for the radius. We achieved about a 17.4 times smaller spot than last week.
Here's a picture of everything we used to conduct this experiment.